Last night I had this experience that kind of perfectly frames what we're talking about today. Put my music library on shuffle, and there was this one specific song I was waiting to hear.
Oh, I do that all the time. You're just like sitting there waiting.
Right, and I found myself just sitting on the couch counting. Like, how many tracks are going to play before, that one specific song finally comes up?
And the funny thing is, the answer to that changes every single time you do it. One night you try it, and maybe it's the third song. You try it another night, and you might be waiting until, I don't know, the 11th song.
Yeah, totally. But what really stood out to me as I was sitting there was that I completely stopped tracking which specific songs were actually playing.
Like the artists or the genres.
Exactly. I didn't care if it was a jazz track followed by pop or rock followed by acoustic. All of that rich, messy detail just kind of faded away. I just kept one single number in my head. How many songs until the one I wanted?
And that instinctive move taking a very messy, unpredictable sequence of events and boiling it all down to just a single number that you actually care about, that's exactly the mechanism we are looking at today.
It's a surprisingly universal feeling.
Right, because the shuffle hands you this complex random outcome, but you instinctively extract just the one piece of numerical information you need.
I realize I do this constantly in everyday life. If you're waiting for a friend to reply to a message, you probably count how many other texts you receive in the meantime.
Yeah.
Or if you're flipping a coin, you just count the heads. It's the same mental move every single time.
It really is.
And that is why today we are looking at a stack of statistics lecture notes, specifically from an intro probability course, to decode something called discrete random variables. Our goal here is to see how this mathematical toolkit completely changes how you view everyday uncertainty.
Yeah, because in probability, that number you're holding in your head, it gets a formal name and a very specific toolkit. Whenever we run a random experiment, it hands us an outcome. But what we usually want to work with isn't the raw outcome itself. We want a number derived from it. Think about, some of the universal examples. If you toss 3 coins, you usually just care about the total count of heads.
You're not logging the exact sequence of heads and tails.
Exactly. Or if you roll 2 dice, you want to know the total sum showing on the faces. You don't really care which die showed a 3 and which showed a 4.
Or if you're playing a game of chance with friends. Ultimately, at the end of the night, you just care about the dollars won or lost. You don't care about every single hand played.
Right. In each of these scenarios, there's an underlying rule at play. We take the raw outcome in, and we get a number out.
And that rule is what we formally define as a random variable, right?
That's it. In the math, we represent it as a function. You will usually see it written with capital letters, like capital X, Y, Z, or W.
Okay, so capital letters.
Yeah. And this function, let's just call it X, it maps from the sample space S, which contains all our possible raw outcomes, to the real numbers R. It feeds in an outcome and spits out a number.
Wait, so if the function is just a rule, like count the heads, the rule itself isn't actually random. The rule is completely fixed.
Exactly.
The variable only inherits its randomness because the underlying outcome feeding into it from the random experiment is random.
That's a crucial distinction. The randomness lives entirely in the random experiment. The variable is just a consistent lens we look through.
Okay, that makes sense.
And depending on what kind of numbers the function spits out, we categorize the random variable into one of 2 types. If the possible values form a listable set, values like 0, 1, 2, 3, we call it discrete.
Right.
But if the values can be anything across a seamless range, we call it continuous.
So just to make sure I had that distinction clear, counting the number of heads in 3 coin tosses is discrete because the answer can only be exactly 0, 1, 2, or 3. You can physically list them. But if we were looking at tomorrow's high temperature, that would be continuous because it could be any value across a range right down to the decimal point. You can't list every single possible temperature.
Spot on. And our focus for this entire discussion is strictly on the discrete case. We are working with sets we can actually list.
Okay, so to see how this function works in practice, let's look at the classic 3 coin tosses. Before we apply any rules or numbers, let's just, observe the random experiment itself.
Sure. So if you flip a fair coin 3 times, how many possible sequences are there?
Okay, let me think. There are 2 choices for the first toss, 2 for the second, and 2 for the third.
Mm-hmm.
So 2 times 2 times 2. That gives us 8 possible sequences.
Right.
Starting from all heads, 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 then maybe heads, heads, tails, and going all the way down to tails, tails, tails.
Exactly. We have 8 sequences. And because the coin is fair, these are 8 equally likely outcomes. Each specific sequence has a probability of 1/8. Now we introduce our random variable. Let capital X be the number of heads. To find the value of X for any outcome, we just read the sequence and count the heads.
So if the random experiment hands us the sequence, heads, tails, heads,
Mm.
the function feeds that in and spits out the number 2.
Mm.
If the sequence is all tails, X equals 0. If it's all heads, X equals 3. But I'm noticing something about how this function behaves.
What's that?
Well, the sequence heads, tails, heads gives X equals 2, but so does heads, heads, tails, and so does tails, heads, heads.
Right. The function squished several distinct outcomes into one single value. It collapsed all the details you didn't care about, the specific order of the coin flips, and it just preserved the count.
But by collapsing those details, we aren't just simplifying the picture, we're sort of building an entirely new space to work in, right? Instead of juggling all 8 original sequences, we just have a small list of numbers.
That's exactly it. Grouping these outcomes creates a new, smaller sample space. We call this the value space S sub X.
S sub X.
Yeah. Instead of a sample space containing 8 sequences, our value space S sub X just contains the values 0, 1, 2, and 3. Each of these values acts like a basket, scooping up the specific outcomes that produce it.
Oh, I like that. So the event X equals 2 is really just a basket holding those 3 specific sequences I mentioned. Heads, tails, heads, 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 tails, and tails, heads, heads.
Exactly. And since each of those sequences has a probability of 1/8, and there are 3 of them in the basket, the probability that X equals 2 is 3/8.
Wow, okay. We just moved from listing raw outcomes and their individual chances to finding the likelihood of our numerical values.
Right. And when we systematically do this for every possible value in the value space S sub X, we create a new function. We write this as lowercase f of X.
This f of X represents the probability that X equals X. So earlier we found that f of 2 is 3x.
Yes. This lowercase f of X is called the probability distribution function, or the PDF. Yep. In the discrete case, you will also frequently hear it called the probability mass function, or PMF. They describe the exact same object. I'll use PDF here, but it is helpful to know both terms.
So the PDS gives us the probability at each specific point. But how do we know if the PDF we've built is actually mathematically valid? Are there, like, rules that has to follow?
It follows 2 intuitive rules. First, every f of X must be at least 0.
Right, because you cannot have a negative probability of an event happening.
Exactly. And second, if you add up the f of X for every possible value, they must all sum to 1. This simply means that the random variable has to take on some value from our list. We have accounted for 100% of the possibilities.
Okay, looking back at our coins, we can check this. The probability of 0 heads, f of 0, is 1/8.
Right.
For 1 head, f of 1 is 3/8. For 2 heads, f of 2 is 3/8. And for 3 heads, f of 3 is 1/8. If we add those up, 1 plus 3 plus 3 plus 1, we get 8/8, which is 1. The rules hold.
Perfect. If you visualize this distribution, picture it as a histogram. You have bars rising up from the values 0, 1, 2, and 3 on the horizontal axis.
Okay, I'm picturing it.
The bar at 0 is short. The bars at 1 and 2 are tall. The bar at 3 is short again. It is tall in the middle and short on the ends. That physical shape you are visualizing, that is the distribution.
This makes total sense for coins, but I want to apply this to an everyday scenario to see the mechanics in a different context.
Sure, let's do it.
Let's say a school is ordering computers. A shipment of 20 laptops arrives, but unknown to the school administrator unpacking them, 3 of those laptops are actually defective. The school just takes 2 laptops at random from this shipment to use in a classroom.
Okay, great example. We first need to define our random variable. Let capital X be the number of defective laptops the school ends up with.
Since they're only buying 2 laptops, the possible values for X are 0, 1, or 2.
Right.
So our value space S sub X is just 0, 1, 2. To find the PDF, f of X, we need to determine the probability of getting exactly 0, exactly 1, or exactly 2 defective laptops. I assume this involves, like, counting all the possible combinations for how they could pick 2 laptops out of the 20.
We do rely on combinations for that, yes. We first determine the total number of ways the school could choose 2 laptops out of the 20 available. The math gives us a specific number. The size of S is 190.
Okay.
There are 190 total ways to choose.
So we have 190 total possible outcomes. How do we distribute those to build our PDF? Like, what is the probability they get lucky and pick 0 defective laptops?
To find f of 0, we count the ways to pick 2 laptops entirely from the 17 good ones. And it turns out this happens most of the time. The vast majority of those 190 combinations are perfectly fine.
Well, that is a relief for the school. They get 0 defective laptops most of the time. What about getting exactly 1 defective laptop?
For f of 1, they pick one of the 17 good laptops and one of the 3 defective ones. This happens a smaller chunk of the time. It is less likely than getting 2 good ones, but is still a realistic possibility you'd want to plan for.
Right. And f of 2.
Yeah.
That's the absolute worst-case scenario, where both laptops they pull out of the box are defective.
Yeah.
I imagine whoever unpacked those is having a terrible day.
Seriously. They would have to pick 2 laptops exclusively from the 3 defective ones in the entire shipment. There are very few ways to do that. The probability f of 2 means it happens very rarely. Only a tiny fraction of the time will they have luck that bad.
Even without listing all the exact fractions, the underlying machinery is identical to the coin tosses. The probabilities for 0, 1, and 2 defective laptops will still sum perfectly to 1.
Exactly.
It is the exact same math, just telling a totally different story.
Yeah.
But, the PDF, lowercase f of x, it seems really specialized. It is a tool for when you want to know the probability of exactly one specific value. In real life, I rarely ask questions that way.
You're getting at a major limitation of only using the PDF. We often want to know the probability of a threshold being met.
Right. Like if I am budgeting for a project, I don't care about the probability of spending exactly $50. I care about the probability of spending $50 or less. I need to know a running total.
All right.
How does the map handle that shift in thinking?
This brings us to the second tool in the notes, the cumulative distribution function, or CDF.
The CDF.
Yes, we write this with a capital letter, capital F of x. The CDF is defined as the probability that x is at most x. It is a running total of the PDF. It systematically adds up every f value at or below your chosen point x.
Okay, so going back to our 3 coin tosses, if we want the probability that x is at most 2 heads, we evaluate capital F of 2.
Exactly.
We just take our PDF values and add them up. It would be the probability of 0 heads plus the probability of 1 head plus the probability of 2 heads.
Let's do the addition. 1/8 plus 3/8 plus 3/8, that gives us a running total of 7/8. The probability that x is at most 2 heads is 7/8.
I can intuitively verify that. The only way to not have at most 2 heads is to get exactly 3 heads, which has a probability of 1/8. All the other possibilities must account for the remaining 7/8.
That's a great way to check it.
So while lowercase answers what is the probability exactly here, capital F answers how much total probability has piled up at or below this point.
Spot on. Now, if you visualize the PDF as a histogram with bars, you need a different mental image for the CDF. We describe the physical shape of the CDF as a staircase.
A staircase. Walk me through how we construct that shape.
Imagine a graph where the horizontal axis represents the values of our coin toss. So from negative numbers through 0, 1, 2, 3, and onward. The vertical axis is our running probability total, capital F of x, which goes from 0 to 1.
Okay.
Before we reach the value 0, no probability has accumulated at all. The graph is perfectly flat on the horizontal axis at 0.
You're walking along the flat floor, and then you hit the value 0 on the axis.
Right. The moment you hit 0, the running total jumps up by the probability of getting 0 heads, which is 1/8. You take a sudden vertical step up to a height of 1/8.
Okay, this is where I want to clarify something because the visualization can be tricky. What happens to the graph between 0 and 1? Say at 0.5 heads or 0.9 heads?
Nothing happens. Since this is a discrete random variable, no outcome actually lives at 0.5. You cannot physically flip half a head.
Right.
So no new probability gets added to our running total. The graph stays perfectly flat, holding steady at that height of 1/8.
So at 1.5 heads, it's flat because no outcome actually lives there. It holds steady until the next real value. It literally is a staircase, not a ramp.
Exactly. It is not a ramp. It only moves in discrete, sudden jumps. When you finally reach the value 1 on the horizontal axis, you add the probability of getting exactly 1 head, which is 3/8.
Okay.
So from your current height of 1/8, you take a vertical step up of 3/8, landing at a new flat stretch at the height of 4/8 or 1/2.
And then it stays flat again until we hit 2. At 2, we add another 3/8, jumping up to 7/8. It stays flat again until 3, where we add the final 1/8, jumping up to a height of 1.
Yep.
From there on out, Does it just stay flat at 1 forever?
It stays flat at 1 forever because we have accumulated all 100% of the probability. There is nothing left to add.
Makes sense.
Any valid cumulative distribution function, any staircase we build this way, has 4 strict properties it always obeys.
Okay.
First, the function always lives between 0 and 1.
Which physically makes sense. You can't have a running total of probability less than 0, and you can't have more than 100% probability of an event happening.
Second, the function is non-decreasing. As you move to the right along the horizontal axis, the staircase only ever goes up or stays flat.
Because we are only ever adding more probabilities to our running total, we never encounter a negative probability that would force us to step down.
Exactly. Third, if you look far to the left, before any values have occurred, the function heads to 0. And far on the right, after all values have occurred, it heads to 1.
It starts at the floor, because nothing has happened yet, and finishes at the ceiling, because eventually all possible outcomes are accounted for.
Right. And the fourth property is a bit more technical. The function is rate continuous. This simply means that the jumps happen exactly at the values of x.
Oh, so if I am drawing this, the solid dot is at the top of the step. The moment I arrive at the value 1, I immediately take the step up to the new height. I don't wait until just after 1.
Correct. We now have 2 perspectives on the exact same information. We have the individual probabilities at each point, the PDF, and we have the running total staircase, the CDF.
Since they contain the identical underlying information, can I run the process in reverse? Like, if I am only handed the staircase, can I work backward to figure out the individual probabilities that built it?
You absolutely can. You do it by measuring the jumps. The height of any sudden jump on the staircase is exactly the PDF at that value. The formula for this is straightforward. F of x equals 1 running total minus the running total just before it. You are simply calculating the difference to find the new piece of probability that was just added to the pile.
Let's trace an example of reversing the process just to see this in action.
Yeah.
Let's say we're handed a completely new random variable, w. We don't know the story behind it. We just know its possible values are 0, 1, 2, 3, and 4.
Right.
And we are given its CDF staircase. The running total climbs like this: 1/8, 3/8, 5/8, 7/8, and finally 1.
Okay, so we want to recover the original PDF, f of x. We evaluate the jumps. Let's find f of 1.
Right.
To find the probability at exactly 1, we look at the running total at 1 and subtract the running total just before it at 0. The running total at 1 is 3/8. The running total at 0 was 1/8.
So we take 3/8 minus 1/8. That gives us 2/8, which simplifies to 1/4. The jump at 1 is 1/4. So the probability that w equals 1 is 1/4.
Exactly. We just keep doing that for every value. If you subtract each step from the one after it, you will find that the individual probabilities are 1/8, 1/4, 1/4, 1/4, and 1/8.
You can picture this visually, too. Instead of a histogram with thick bars, picture a stem plot.
A stem plot, yeah.
You just draw a vertical spike rising up from each number on the horizontal axis. The height of that spike is exactly equal to the height of the jump on the staircase.
That's a great way to look at it. Once we understand how to navigate this staircase, we can use it to answer much more specific questions without having to add up a bunch of individual numbers. You can read the probability of any interval just by finding the difference between CDF values.
So if I want to know the probability of an event falling within a specific range, I just subtract the running total at the bottom of the range from the running total at the top.
That is the core idea. But this is where we must be incredibly precise. Because we are dealing with discrete variable staircases with sudden jumps and flat stretches, the exact wording of an interval makes a massive difference.
It's all about the endpoints, right?
Yes.
Because if a value is included in the interval, we have to include its jump. If it is excluded, we miss the jump entirely. It's like a speed limit sign. If a sign says under 60, does that mean you get a ticket right AT 60? The boundary matters.
Perfect analogy. The phrase less than explicitly excludes a value. The phrase at most includes it.
Right.
If I ask for the probability that w is less than 2, I am looking at the running total right before 2. I do not include the jump at 2. But if I ask for the probability that w is at most 2, I must include that jump. When the values are discrete, being on the boundary completely changes the math.
Okay, so if we line up our two tools side by side to recap, we have the PDF, lowercase f of x. This tells us the probability at each specific value. It is the height of the histogram bars, or those vertical spikes.
Right.
And then we have the CDF, capital F of x. This tells us the probability up to a specific value. It is the height of the running total staircase.
Two views of the exact same information. You can sum the bars of the PDF to climb the stairs of the CDF, or you can measure the jumps of the CDF staircase to get the bars of the PDF back. You can travel effortlessly in both directions depending on what kind of question you are trying to answer.
Everything we have discussed today, all this math, it relies on one fundamental assumption, that our possible values form a tidy list. 0, 1, 2, 3. We can list them out, and we can measure the distinct sudden jumps between them.
That assumption is exactly what defines a discrete random variable. In our next discussion covering Lecture 6, we will remove that assumption.
Oh, okay.
We will ask what happens when the variable x isn't a tidy list anymore.
Like the temperature example from earlier.
Right. When x can be any value in a continuous interval, the math has to adapt. You can't stack a discrete bar of probability at infinitely many points along a number line.
If you did, they would all have 0 probability.
Exactly. In the continuous world, probability becomes the area under a curve. Our discrete sums will become integrals. And that rigid step staircase of the CDF will smooth out into a flowing continuous line.
Same underlying ideas, but an entirely new set of mathematical tools to handle the infinite detail. Well, the next time you put a playlist on shuffle and you are sitting there waiting for that one song, consider the math happening underneath. You aren't just patiently waiting. You are moving along an invisible staircase, gathering a little more probability with every track that plays.
Yeah,